Hello everyone. So in the previous part of the lecture, we had started our discussion of 2D elasticity, and near the end of the lecture, we had gone on to uh, discuss how important when proceeding along the route of the Airy stress function approach, it is to consider the compatibility equations. So we'll continue from that point, and accordingly our first job in today's lecture will be to consider the compatibility equations and see what simplifications are possible and what we can do when proceeding on the route of this Airy stress function approach. So the first of the compatibility equations, let me use the white color. So the first of the compatibility equations involves the epsilon xx, epsilon yy, and the epsilon xy. We're going to write that down. So as written, you can see that other than the fact that each of these strain components, epsilon xx, epsilon yy, and epsilon xy, particularly within the consideration of plane stress, has no dependence on z, other than that there is no simplification here. So as written, it remains. Okay, but uh, considerable simplifications will be possible in the subsequent compatibility equations, as you will soon see. So the next one is del square epsilon yy del y square plus del square epsilon zz. Sorry, I made a mistake here. This should be z square del square epsilon yy del z square plus del square epsilon zz del y square is equal to twice del square epsilon yz del y del z. Now we had already seen in the previous lecture that epsilon yz is equal to 0. We have also seen that epsilon yy, because it is a function of sigma xx and sigma yy, which in turn are functions only of x and y, the z dependence of epsilon yy is 0. Okay, so it is not there. Therefore, when we differentiate epsilon yy with respect to z, it gives us 0. So this term vanishes, this term is also vanishing. So this is just giving us that del square epsilon zz del y square is equal to 0. The next compatibility equation is del square epsilon zz del x square plus del square epsilon xx del z square is equal to twice del square epsilon zx del z del x. Again, we have already seen that epsilon zx is 0. We also know that epsilon xx, just like in the previous case of epsilon yy, which was a pure function of x and y, this epsilon xx is also a pure function of x and y. It has no z dependence, therefore this term vanishes. So overall what we have here is that del square epsilon zz del x square is equal to 0. Next, we have del square epsilon xx del y del z is equal to, so here we have del x minus, so I like to write it in this fashion, minus del x plus del y plus del z, and then fill up the strain components. So it's just my preferred way of writing these things because it helps me to remember. You follow your own method. Okay, so from this equation we note that just like before, when we said that epsilon xx and epsilon yy were independent of z, in a similar fashion epsilon xy here is also independent of z. So this term vanishes. Epsilon zx by itself is 0, epsilon yz by itself is 0. And finally, the epsilon xx may have a dependence on y, so this derivative with respect to y is fine, but it also has a derivative with respect to z, and we have already seen that epsilon xx is only a function of x and y, so this term also vanishes. So overall what we have from here is a 0 equal to 0 form, so that is identically satisfied. Next, the next compatibility equation is in terms of the epsilon yy. So this is del z del x is equal to, again just like before, we follow a similar strategy for writing this out. So this here is yz, this is zx, and this is xy. And again, this term vanishes because epsilon xy is not a function of z. Epsilon zx by itself is 0, epsilon yz by itself is 0. And this epsilon yy is not a function of z, so this term vanishes. So again, we have a 0 equal to 0 form. And finally, we have del square epsilon zz del x del y is equal to del z. Again, like before, we write it out. Epsilon yz, epsilon zx, and epsilon xy here. Again, epsilon xy not a function of z, epsilon zx by itself is 0, epsilon yz by itself is 0. Epsilon zz, mind you, is not 0. And we have already said that epsilon zz is a function of x and y. So this term on the left hand side is not 0. So all that we can say here is that this equation simplifies to del square epsilon zz del x del y is equal to 0. So you see, the only equations that are remaining really are this first equation, this one involving the epsilon zz, and this final one involving the epsilon zz. The remaining two equations are just 0 by 0 form. These are trivial. Alright, now what we are going to do is to consider only the first of these equations. Okay, so in this fashion, because we are not accounting for what is happening with the epsilon zz, we are just letting it be, and as we move forward, you will see that the information that is embedded in this equation, only that is utilized. Therefore, what we are doing as far as our mathematical formulation is concerned, this is only an approximate theory. Okay, so layer by layer you are seeing that what kind of approximations are embedded within this general theory. And despite all of this, let me just tell you that the plane stress theory is very much successful in capturing a lot of real physical situations. Okay, so there is a real strength to these approximations. All right, so without any further ado, let us actually go on and utilize the first of these strain compatibility equations. So this is where we are going to really start our formulation steps with. Okay, now this one is from the compatibility equation. What we are going to do now is to include here. So the idea is that everything must be included. Okay, we need to include everything that we know. So within this, we are first going to include the information from the constitutive law. So let's take a look here. So back on this page 2, we had obtained the simplified versions of epsilon xx and epsilon yy, simplified under the consideration of plane stress, where the terms involving the sigma zz, they vanished. So let's substitute these things as well as this expression of epsilon xy in terms of sigma xy. Okay, so we are going to substitute and actually let us number these equations. It will be easier to keep track of these things. Okay, so this one is 1, this is 2, this is uh, this is 3, this is 4, and let's not call this 5 and 6. Okay, so you understand that epsilon yz is 0 and epsilon zx is 0. Now um, let us come to uh, this equation and call this, rather this, as uh, equation number. So I stopped here at 4, so this is 5. Let's call this 5. Okay, so what we are going to do is to substitute in equation number 5 the information that is present in equation numbers 1, 2, so equation numbers 1, 2 and 4. Okay, so uh, using 1, 2 and 4 in 5, that's what you're going to do. So this is del square del y square. This epsilon xx is 1 by e sigma xx minus nu sigma yy. That 1 by e is a constant. Okay, so we might as well take this out of the second derivative, and what we'll have inside is this sigma xx minus sigma yy. Next, similarly, we'll have the 1 by e coming out of this second order derivative, this del square del x square, and inside for the epsilon yy we have this sigma, sorry about that, sigma yy minus nu sigma xx. And finally for this one we have 2 into 1 plus nu by e. So this part is coming from the 1 by twice g, and this is del square del x del y sigma xy. All right, now you see from all of these terms we have the 1 by e cancelling out. Okay, so what we are going to do next is to collect uh, the terms involving the sigma xx. So we have a sigma xx here and we have a sigma xx here, but please note that this is a derivative with respect to x square and this is the derivative with respect to y square. Okay, so uh, what we have here is something like this: minus nu del square del x square plus del square del y square, that operating on sigma xx. In a similar fashion, what we have next is for the sigma yy, which is present here and present here, we have del square del x square minus nu del square del y square operating on sigma yy, and the right hand term that just remains as it is, except that the 1 plus 1 by e term that gets cancelled out. Okay, so now what we are going to do is on the left hand side for this term we are going to add a del square del x square, and we are going to subtract that out also. Okay, so we are going to add a del square del x square and we are going to subtract out a del square del x square, so that effectively this remains as it is. So if we do that, then what we are going to end up with is minus 1 plus nu del square del x square plus del square del y square. Sorry about that, a slight mistake here. So this is a sigma xx. So that I obtained from the minus of del square sigma xx del x square, which was present here, and from the plus which I have uh, included, I will get that as del square del x square plus del square del y square, this entire thing operating on sigma xx. So you please note that from this term I'm getting this term just by kind of artificially introducing the del square sigma xx del x square term. Okay, next I'll do a similar sort of thing here also, but I'll do this involving the del square del y square. So I will add a del square del y square here and subtract a del square del y square. So effectively it remains the same, just the form becomes somewhat more symmetrical. Okay, so those of you who can see a bit ahead will perhaps appreciate the fact that at least one part of the motivation of proceeding like this is to introduce the Laplacian operator here. So we have the Laplacian operator being introduced here, the Laplacian operating being introduced here. Right, and the right hand side just remains as it is. Next, what we'll do is to write this in a slightly cleaner fashion like this. We'll take this 1 plus nu common with this 1 plus nu. So what remains inside is this del square sigma xx del x square plus del square sigma yy del y square. Okay, so please note that there is no Laplacian going on here. Okay, so this is just as it is. This however is a Laplacian and this is a Laplacian. Okay, so what we can do is we can write them together as the Laplacian operating on sigma xx plus sigma yy. So that is considerably shortened. Okay, so the left hand side term is done. On the right hand side this remains. Let's call this equation number 6. Now just looking at equation number 6, it looks somewhat symmetrical, but what do we do with it? Okay, it's good that we have utilized our compatibility equations, and within it we have embedded the information from the constitutive laws. But what after this? Okay, so the next plan is to incorporate within it the information from the stress equilibrium equations. Okay, so please note that earlier when we said that when we started all this discussion within the root of Airy stress function, our motivating equations were the stress equilibrium equations. But once we have started this formulation, we have not actually utilized the stress equilibrium equations till now. Okay, so it's time that we do that, and you'll see in a moment that utilizing the stress equilibrium equations will actually help us in putting this equation number 6 in a slightly more in a considerably more convenient form. Okay, so let's do that. So let's go to the next page and consider the stress equilibrium equations. And this time, as I had promised earlier, we are going to include the body force terms. Okay, so even though our motivation was set up by not considering the body force term because we just wanted to have a simple version to talk about, now we are going to utilize this body force term. Please note that I'm no longer writing this as rho bx unlike the stress chapter. I'm just writing this as fx. Okay, I hope you won't mind. So the next one is del sigma xy del x plus del sigma yy del y plus fy. All right. So what we do here is a little trick motivated by what we have in equation number 6. You see, in equation number 6, we have these terms involving the second derivative of sigma xx with respect to x. Okay, so motivated by that, what we'll do is we'll differentiate the first of these equations with respect to x. So that will give us a del square sigma xx del x square very nicely. So perhaps we can utilize this in equation number 6, and as we'll see, this is del x del y plus, or we can write this on the right hand side, minus del fx del x. Okay, so let's call this equation number 7. Similarly, we'll differentiate the second of the stress equilibrium equations with respect to y, motivated by the desire of introducing a del square del y square for the sigma yy term. If we do that, we obtain this equation, and on the right hand side I have the del fy del y. Let's call this equation number 8. Now, as you can almost guess, even before I write anything more, I'm going to add up this equation number 7 and 8. Okay, so if I do that, what I obtain is del square sigma xx del x square plus del square sigma yy del y square. So you see, these two terms are very much present in equation number 6. Okay, and what I have here is this plus twice del sigma xy del x del y, where of course I have utilized the equality of these two terms. Okay, so I'm saying that the second order partial derivatives are continuous, which is why the order of the derivatives do not matter. Okay, so this is del fx del x minus del fy del y. All right, now and let's call this equation number 9. Now if we utilize this equation number 9 back in equation 6, okay, so use 9 in 6, so what do we obtain? So you see, these two terms, so we are going to replace these two terms by whatever is left here. So we have a minus 1 plus nu, so this one, and then whatever is inside this bracket, that is basically this thing, minus twice del square sigma xy del x del y minus del fx del x minus del fy del y, and what remains in equation number 6 is this one. So the Laplacian of sigma xx plus sigma yy, and on the right hand side of equation 6 I have this term twice 1 plus nu del square sigma xy del x del y. Now very nicely you see, if you just consider this first term on the left hand side, this minus and minus is a plus. This is 2 into 1 plus nu del square sigma xy del x del y. on the right hand side also I have the exact same term. So this first term on the left hand side, it cancels with the first term on the right hand side. Okay, so if I just simplify this algebraically, what I will obtain is del squared sigma xx plus sigma yy. So the Laplacian operating on that, that's equal to, I transpose these two terms to the right hand side, taking care to carry along the 1 plus nu. This is going to be minus, because this minus and this minus was already a plus on the left hand side. So on the right hand side this becomes a minus, and then I have the del fx del x plus del fy del y. Okay, so let's call this equation number 10. So now we have this equation within which the information from the compatibility equation is embedded, the information from the constitutive law is embedded, and the information from the stress equilibrium equations are embedded. And mind you that all of this has been done starting out with the motivation of using the Airy stress functions. But till now, very surprisingly, we have not yet introduced this Airy stress function. Okay, so it is high time that we did that. Now, if we just go back to that motivating page of considering the Airy stress function, this page number 3, we have written down these three expressions. All right, and these were written down by keeping in mind these simplified versions of the stress equilibrium equations, where for the purpose of illustration and clarity of the first discussion, the preliminary discussions, we had neglected the body force terms, but now we are considering the body force terms, right? So how does it work? Okay, so it works through a little bit of a special consideration, and that consideration is that these, for the Airy stress function to work, we say that these body forces, these body force components fx and fy, they must be derivable from a potential function. So that seems like a rather complicated thing to say. What we basically mean physically is that the body force must be conservative in nature. Okay, so that's what we are going to discuss next. So we consider body forces that are conservative in nature. And as I said, this basically means that we are going to be able to write the fx as the gradient of some scalar potential v. So this v is some scalar potential. Similarly, the fy is the gradient of some scalar potential. So basically what we are saying here is that the force vector, or the body force vector f, that is equal to minus grad of this scalar potential v. Okay, I'm sure from your studies of physics this will ring a bell. Okay, so basically what we are saying here is that the Airy stress function approach is going to work, of course, very easily if the body forces are zero, and even if the body forces are not zero, as long as they are conservative in nature, in which case this fx and fy can be represented in these terms, in terms of the scalar potential, it will still work. Okay, so let's see what form the stress terms are going to be if this is the case with the body force terms. So for that we are again going to take a look at the stress equilibrium equations, but this time considering the body force terms. So basically we are just rewriting these things. Okay, so what we got from this one. Okay, so we are not going to consider 7 and 8, rather we are going back to the source. Okay, so we are just going to rewrite that. Of course, this time this fx we are going to replace by this one, and the y component of the stress equilibrium equations, which involves the Fy sorry, this del V del y. Alright, so overall what we basically have from here is that we have a term involving the del x, that is sigma xx minus v, plus del sigma xy del y is equal to 0. So that's a more convenient way of writing it. And here it's del sigma xy del x plus the del y terms get clubbed together. So it's sigma yy minus v. Okay, now if you just compare with what we had obtained earlier. Okay, so see here, when we had only the sigma xx setting and the sigma yy setting without the v terms, in the very next page we were able to write this down. Okay, so now the only difference is that here we have a del x term along with a minus v, and here we have a del y term along with a minus v. That's the only difference. So if that is so, then can we not write this thing again just by saying that instead of the sigma xx we have a sigma xx minus v and the sigma yy minus v. That's the only difference, and we can still use the same forms that Professor Airy had first written down back in the 19th century. All right, so so from here what we are going to say is that sigma xx minus v, let that be del square phi del y square, the sigma yy minus v, let that be del square phi del x square, and the sigma xy, well, that remains unchanged as before. It's del square phi del x del y. So if we substitute these particular mathematical forms back here, we'll see that both these equations are identically satisfied. And let's actually name those equations, number those equations. So this was the last equation number 10. We're going to say that this is equation number 11 and this is equation number 12. Okay, so what we are going to do is we have defined these forms. So we go back to this equation number 10 and substitute those forms in terms of the Airy stress function phi. That's all that we have to do. So we rewrite this equation number 10. Okay, so just this equation number 10, we just rewrite it. So this is a del square sigma xx plus sigma yy. Take a look again, minus this entire term. And please note here that this fx is now minus del v del x. So overall this is going to be a minus del square v del x square. This fy is minus del v del y, so it's going to be minus del square v del y square. Okay, so that's the only difference there is. And we also note that the minus and the minus that we had here and the minus that we had here, that just went outside and cancel this minus that was present. Okay, so when we substitute fx equal to minus del v del x and fy equal to minus del v del y, that minus just cancels out with this. Okay, so overall we have this kind of a nice form. And when we substitute the sigma xx, these terms here, let's see what it gives us. Okay, so let's do that on the next page. Let's not clutter this page anymore. So del square, so sigma xx is v plus del square phi del y square, v plus del square phi del y square. Similarly, the sigma yy is v plus del square phi del x square. This term is over, and on the right hand side I have this term, which is basically 1 plus nu. Just look at it carefully, this is just the Laplacian of v. Okay, so we'll write that. So this is basically giving me twice Laplacian of v, because this is twice v. The 2 goes outside, this Laplacian acts on the v, and this term and this term, they are together making up a Laplacian. So we have the Laplacian outside and I have another Laplacian inside acting on the phi. So overall what I'm going to get is a del 4 phi. So this is the Laplacian of the Laplacian. So it's like the bi-Laplacian, sometimes referred to as the, or very commonly referred to as the biharmonic operator. And on the right hand side, I'm going to get so this is going to be nu minus 1. So I just write it like this. All right. So please note that this is this del 4 phi, and this del 4, it is the biharmonic operator. Okay, so the Laplacian acting on itself is sometimes referred to as the bi-Laplacian. This is more common. Okay. So overall, this equation, okay, so in the special case that the body forces vanish or the del square V is equal to 0, so if uh, body forces vanish, okay, or del square V is equal to 0, then del 4 phi is equal to 0, and please note that this is what is referred to as the biharmonic equation. Okay, one of the most important equations in linear elasticity. And its solutions will be referred to as the biharmonic solutions. So you see, overall what we have managed to do is uh, we have so it's I mean it may look rather as steps of a series of algebraic manipulations, but through those manipulations what we have managed to do is to encapsulate within just this one very elegant looking equation, this biharmonic equation, the information which is conveyed by, first of all, the compatibility equations, uh, the constitutive law, the stress equilibrium equations. Okay, so everything is included in this thing. Okay, so so the idea is that if we solve this equation for particular physical situations, provided boundary conditions and everything, so we should be able to get very nice solutions to real physical problems. So with this, we are going to end this part of the lecture, and we are going to continue our discussions of the Airy stress functions. In fact, a large part of the remaining part of this course will be associated with solutions of this biharmonic equation. All right, thank you very much.